Okay, so now we look at the center of mass. The center of mass of an object or a collection of objects is that point where it is as if the entire object, the mass of the entire object is concentrated at that point. So it's that location in one object or in a collection of objects where the object behaves as if its entire mass is concentrated at that point. It's also the point where we can balance something. So, for example, if we have a seesaw, and let's say we have a seesaw here like this, and it's balanced at the center. Let's suppose there's a 20 kilogram person sitting here, and at an equal distance there's another 20 kilogram person sitting. So it's still in balance because the downward force on the right side is exactly the same as the downward force on the left side. But let's suppose that instead of having a 20 kilogram person, we had here a much larger person, let's say 40 kilograms. Now this side is evidently heavier and is going to tilt lower, and this is going to go upwards. So it's no longer balanced at the center. Now if we change the situation a little bit and we have the same seesaw and we have the same two persons, so it was here, this person is 20 kilograms and is still at the same place, but this person moves a little bit to the left and is sitting somewhere here. Now you would intuitively know, and you may have most likely experienced that now it could be in balance. So even though on the right hand side we have more mass as compared to the left hand side, but it's still in balance. And the reason is that this mass is closer to the fulcrum or the support as compared to this one. So the masses, to have a thing in balance does not mean that the masses on both sides are equal, but it means that something else is equal. And that something else is what we call the torque. So this point where it balances is the center of mass. So in this case, where the two masses were equal, well, in the previous case where the masses were equal, then the center of mass would have been in the middle. But when one of them is heavier, then this point is not the center of these two masses. It's still the center of the stick, but not the center of the masses. But it is still the center of mass because it's balanced over here. So this thing torque, before we go into the torque, let's have another small example on what torque would mean. So consider a person standing holding a meter stick. Let's suppose that's a meter stick, and it's fairly easy to hold it like that, holding it straight out, sticking out like this, not too hard. But now let's suppose you put a weight on it. Let's just say you put 1 kilogram, and that kilogram is very close to the point of support, so it's still not going to be too hard to hold it up. But if the same person holding the same meter stick with the same 1 kilogram mass, but the mass is attached over it, is put at the end of the stick, then it's going to be very hard for him to hold it up over here. It's going to sort of sag lower. So if you're holding it like this, you attach a weight over here, it's not so hard to hold it. But if the weight is attached here, it becomes much easier to bend it. And so the same mass at a bigger distance has a greater twist or a torque. So the torque is the force. In this case, the force is mg times a distance, and the distance is the distance from the support in this particular case. So that's the torque. It's a force times distance, and the same would be here. So if this distance were x1 and this distance were x2, then because m2 is heavier, the force is bigger. In this case, the distance is smaller compared to the other side, but the product becomes the same on both sides. So let's try to solve this, and let's say this is side 1 and this is side 2. Then the torque on side 1, well, this is a symbol for torque. It's the Greek letter tau. So the torque on the left side is going to be the force, which is m1g, that's the downward force here, times the x1, the distance to the fulcrum, x1. And the torque on the other side is going to be m2g, and the distance is x2. And because it's in balance in this condition, the two torques must be equal, and so we have torque 1 equals torque 2, or m1g x1 equals m2g x2, and therefore we can find x2. The g's can cancel out. It's going to be m1 over m2 x1, and so you can find x2 if you know x1. However, there are cases where you don't know x2, and that's what we're trying to find. So here you can place it and balance it. So we're going to try to find a formula that we can use to find the torque. Now, luckily, this thing that the sum of the torque on this side equals the torque on this side, we can rearrange that and say that the sum of the torques is 0. So T1 plus T2, or tau 1 plus tau 2 should be 0, which means the one of them has to be positive and the other has to be negative. Otherwise, they will simply add up. So by convention, if you have a support over here, and if a force acts like this, that tends to cause it to rotate clockwise. So this force is creating a clockwise torque because it tends to rotate it clockwise. This is taken as a negative torque. And if there's another force acting upwards that tends to cause it to turn counterclockwise, torque, so it creates a counterclockwise torque, then that is taken as a positive torque. That's by convention, and we'll follow that. And this is the same thing with regard to angles. So if the angle is measured this way, it's taken as a positive angle. And if we have something that's spinning, we have an angular velocity. If it's spinning like this, we say it has a positive angular velocity. If it's spinning like this, it has a negative angular velocity. So it's a negative torque and a positive torque, a positive angle. Everything counterclockwise is taken as positive. And we'll be doing a lot more of that as we go into rotation. So the torques are 0. So let's go back to this condition, and let's also realize that there is a force upwards here that's holding the whole thing up. So if we try to find the torque at this point, what we did here, tau 1 was to find the torque about this point. So x1 was taken as the distance from here, and x2 was also taken as the distance from here. But if distance from here and from here. But if you want to find the torque about this point, then we'll have a force times this distance will be the torque due to this. This force will act over this distance, so that will create a counterclockwise torque. And this force will act over a much bigger distance, create a clockwise torque. And the good thing is that this would still be should add up to 0. So the general equation here applied to the situation, I'll draw it again over here. We have M2G, and here is the support, and here we have the M1G, and we want to set up the coordinate system so that the y-axis is here, the x-axis is here, and this distance is now x1, and up to here it's x center of mass, because wherever it's balanced, that's the center of mass. And this distance up to here would be x2, and we'll find the torque about this point, and we'll use the same equation, sum of torques is 0. So the first torque is going to be equals torque 1 plus torque 2 plus torque 3. So this is torque 1, it's force times distance. So the force is m1g and the distance is x1, and this force is going to try to cause this stick, the force is downwards, we're going to try to cause the stick to go clockwise. So even though it's not rotating, but it's trying to make it go clockwise. So clockwise means negative. Now this force is trying to push the stick up. If this is the fulcrum, it's trying to push it up, so the stick is going to go counterclockwise. That's a positive torque, and that's going to be equal to the force times x center of mass. The third force is going to try to make it go clockwise again, so it's m2g x2, and they all add up to 0 if F is the center of mass, at the center of mass. Now what is F? So we need the value of F to be able to solve this, and here we use the sum of forces in the y direction, and there is no motion in the y direction because it's balanced, 0, and so we have an upward force is F, a downward force is m1g, and this downward force is m2g equals 0, so F equals m1g plus m2g. It's the sum of the two weights. That's how much this force has to apply. So we replace that here, and we bring it on one side, so we say it's m1 plus m2g, that's the F, times xcm equals, we take this on the other side, so it becomes positive, so it becomes m1 x1 plus m2 x2 times g. So we take the g outside, and we can cancel out the g's because gravity is the same for both of these. This is not much different. xcm will be m1 x1 plus m2 x2 over m1 plus m2, and this is how we would find the position of the center of mass. Now if there were more forces up and down different places, we just add them all up, and so our general equation becomes that the x center of mass is the sum of mi xi, where I is 1 to n. There are n forces. In this case there were only 2 forces, well, 2 extra forces. This is a reaction force over the sum of mi. And similarly in the y direction we would have ycm equals the sum of mi yi over the sum of mi. So this is our equation. These two are our equations. Well, we have the z equation also to find the center of mass. Now let's solve a small example on this. Let's suppose we have an xy coordinate system. Let's suppose there's a a region, a flat surface which is extremely light, so we'll ignore its mass. And we put a mass over here, which let's say is 2 kilograms. And then at a distance of 1 meter, we put another mass. Let's say that's 4 kilograms. This is 1 meter apart. And at 50 centimeters, so it's going to be like here, we put a mass that's 6 kilograms. And this is 0.5 meter. So if they're all on one surface, where is the center of mass? Where, if I want to balance these, it should balance somewhere here. So the center of mass would be here, even if these were 3 points in space. So for example, if you hide this, and this is the moon, this is the Earth, and that's the moon, there'll be a center of mass somewhere in between the Earth and the moon. So there will always be a center of mass between any two objects, irrespective of whether they're connected together or not. Now in this case, let's call this object number 1 and number 2 and number 3. And then the XCM will be the sum of MIXI over the sum of MI. So it's going to be M1, which is 2 kilograms, times X1, which is 0, plus M2, which is 4 kilograms, and X2, which is 1 meter. And the third mass is 6 kilograms, and X is again 0, over M1 plus M2 plus M3. So it's going to be 4 over 12, 1 by 3. So from here to here, we divided in 3 parts. The XCM is going to be somewhere along here at 0.33. And the YCM is going to be the sum of MIYI over the sum of MI. So it's going to be M1, which is 2, and the Y value of this is 0, plus M2, and the Y for here is also 0, and third one is 6, and the Y is 0.5, over 2 plus 4 plus 6, which is 12. And this becomes 0, 0, 6 is 3 over 12. And therefore, the center of mass is X coordinate 0.33 and the Y coordinate 0.25. So it's going to be 0.33 and 0.25. So it's going to be somewhere here. Now, if this is a point in space, you don't have to have a solid object or anything over there.